Hey cosmic explorers, and welcome back to the channel. Today, we're embarking on an epic journey back in time, billions of years ago, to uncover the incredible story of how our home, planet Earth, came into existence. It's a tale of cosmic dust, violent collisions, and immense transformations. So, buckle up, because we're about to witness the birth of a planet. Our story begins not with a bang, but with a whisper of gravity in a vast, cold expanse of space. About 4.6 billion years ago, our solar system was just a massive, swirling cloud of gas and dust. We call these cosmic nurseries nebulae. This particular nebula was primarily hydrogen and helium, remnants from the Big Bang, mixed with heavier elements forged in the hearts of long-dead stars. Think of it like an unimaginably huge, diffuse cloud, far bigger than our entire solar system today. What triggered its transformation? Scientists believe it was likely a shockwave from a nearby supernova, the explosive death of a massive star. This shockwave compressed parts of the nebula, increasing its density. And once a region becomes dense enough, gravity takes over. It's an unstoppable force. Every particle in that cloud, no matter how small, exerted a tiny gravitational pull on every other particle. As these tiny pulls added up, the densest parts of the cloud began to collapse inward, slowly, inexorably, under their own weight. As this colossal cloud collapsed, two crucial things happened. It started to spin faster, much like an ice skater pulling in their arms. And because of this spin, it flattened out into a vast, rotating disk. We call this the Solar Nebula. At the very center of this spinning disk, where most of the mass accumulated, the gas and dust became incredibly dense and hot. This superheated core wasn't quite a star yet. We call it a protostar. For millions of years, the protostar continued to accrete more and more material, getting hotter and denser. The gravitational pressure at its core became immense, reaching temperatures of millions of degrees Celsius. Then, something truly momentous occurred. The pressure and temperature at the core of the protostar finally reached a critical point, initiating nuclear fusion. Hydrogen atoms began fusing together to form helium, releasing an enormous amount of energy. Our sun was born. This ignition unleashed powerful solar winds that blew away much of the remaining gas and dust from the inner solar system, clearing the way for planet formation. With the sun shining brightly, the remaining material in the disk continued its journey of transformation. But the environment within the disk wasn't uniform. Closer to the fiery sun, it was too hot for volatile materials like ice to condense, so only rocky and metallic particles could form. Further out, beyond what scientists call the frost line, both rocky and icy materials were abundant. This explains why the inner planets are rocky and the outer planets are gas or ice giants. So, how did rocky particles become planets? Started small. Tiny dust grains, some no larger than a micron, began to gently collide with each other. At first, it wasn't gravity, but electrostatic forces, like static electricity, that made them stick together. Think of dust bunnies forming under your bed. But on a cosmic scale, over thousands of years, these tiny clumps grew into pebbles, then rocks, then boulders. As they got larger, gravity started to play a more significant role. The bigger chunks began to attract smaller ones, pulling them in. This process of gradual growth by collision and sticking is called accretion. Eventually, these rocks grew into kilometer-sized objects we call planetesimals. The solar system at this stage would have been a chaotic shooting gallery, filled with billions of these small worlds, constantly colliding. Most collisions would have led to them merging and growing larger, but some would have been destructive, shattering bodies into smaller pieces again. It was a cosmic demolition derby, but one that ultimately built planets. Over tens of millions of years, the largest planetesimals dominated their orbits, gravitationally sweeping up more and more material. Our early Earth, a proto-Earth, was one of these success stories. It grew rapidly, accumulating vast amounts of material. The energy from these constant, high-speed impacts was immense. This barrage of impacts, combined with the heat from radioactive decay of elements within the Earth, made our young planet incredibly hot, so hot that it was largely a molten, glowing sphere of rock and metal. In this molten state, a crucial process called differentiation occurred. Like oil and water separating, denser materials sank towards the center, while lighter materials floated to the surface. Iron and nickel, being very dense, sank to form Earth's metallic core. This explains why our planet has a solid inner core and a liquid outer core. Lighter silicate minerals rose to form the viscous mantle, and the very lightest materials eventually solidified to form Earth's thin, outermost layer, the crust. This layering is fundamental to how our planet functions, from its magnetic field to plate tectonics. While Earth was differentiating, it also experienced a colossal event that shaped its future: the formation of our moon. The leading theory suggests that a Mars-sized protoplanet, sometimes called Theia, collided with the early Earth. This catastrophic impact ejected a massive amount of molten debris into orbit, which then coalesced under its own gravity to form our familiar natural satellite. For hundreds of millions of years after its initial formation, Earth continued to be bombarded by leftover planetesimals and asteroids, a period known as the Late Heavy Bombardment. While these impacts were violent, they also delivered crucial ingredients. Many scientists believe that a significant portion of Earth's water arrived from these icy comets and asteroids. As Earth slowly cooled, this water vapor, released from volcanic outgassing and delivered by impacts, condensed into liquid. For millions of years, it rained, filling the vast basins to form our oceans. Simultaneously, volcanic eruptions released gases like water vapor, carbon dioxide, and nitrogen, forming Earth's early atmosphere. This primitive atmosphere was very different from the one we breathe today. It was rich in carbon dioxide but lacked free oxygen. From a swirling cloud of dust, through violent collisions and molten states, Earth slowly transformed into the blue marble we know and cherish. It took hundreds of millions of years for the surface to cool enough, for water to accumulate, and for a stable atmosphere to form. This wasn't the end of Earth's evolution, of course. Life would later emerge and radically change the planet, but that's a story for another time. The creation of Earth is a testament to the power of gravity and the incredible processes that shape our universe. It's a reminder of just how special and resilient our planet truly is. If you enjoyed this cosmic journey, give us a thumbs up, subscribe for more deep dives into science, and let us know in the comments what other cosmic mysteries you want to explore. See you next time.